Am I audible?
Yes, ma'am.
Okay. We'll share the screen. Yesterday, a small bit from 5th unit was remain. Inverse of a function. We have seen these properties for inverse, composition. This composition is associative. In special cases, composition of functions is commutative, and the composition of one-to-one function is always one-to-one, and composition of surjective functions is always onto. Composition of surjective functions is always surjective or onto. Okay. One-to-one means injective and surjective means onto function. Then we saw inverse of a function where f is from x to y, then f inverse is from y to x. Okay. Here f of x is equal to y is always there. Then if f of x is 5x minus 7, then what we get is f inverse as f inverse of, and this f of x is equal to y. So y, what is y is 5x minus 7. From that, what we can conclude is what is f of x. So f inverse of y will be y plus 7 divided by 5 if we perform this f of x, f5x minus 7. Then f inverse of x will be exactly opposite operation of this one, 5x minus 7. It will be y plus 7 divided by 5. Here also we have seen like this, how the inverse is there. A is in f, A is assigned to 3. In f inverse, 3 is assigned to A. In f, B is assigned to 1. In f inverse, 1 is assigned to B. Same case with this. In f, C is assigned to 2. In f inverse, 2 is assigned to C. It is nothing but the inverse of the function. What is there now in next? Same thing is repeated here. G of f of x is equal to x, where g will be the inverse function of f for all x, and f of g of y will is equal to y, where f will be the inverse function of g. Okay, it is going to give us the values of x and y when we perform the composition of inverse function and the original function. Okay, if f is invertible, then there is exactly one function g satisfying this property. The function g is called the inverse of f and is usually denoted by f inverse. F inverse is g. And what is the must condition for inverse is the function f is invertible if and only if it is bijective. It is injective also and it is surjective also. In that case only the inverse is possible for any function. This is because the condition g of f of x is equal to x for all x implies that f is injective, and the condition f of g of y is equal to y for all y implies that f is surjective. Okay, injective means again 1 to 1. When it is 1 to 1, when g of f of x is equal to x, and when it is surjective, that is onto when f of g of y is equal to y. Always keep it in mind that f of x is equal to y and g of y is equal to f of x. Okay, here we have to keep it in mind always. The inverse function f inverse to f can be explicitly described as the function f inverse of y is equal to the unique element x belongs to capital X such that f of x is equal to y. Okay, f of x is equal to y. Ultimately, what we get is f inverse of y is equal to x. Here, f inverse of y is equal to x. When f of x is equal to y, f inverse of y is equal to x. Simply, it is the inverse. And the last bit regarding inverse and all this topic is this one, composition of inverse function. Now, what is there in composition? If f is an invertible function with domain x and codomain y, then f inverse of f of x is equal to x for every x belongs to x, where x is the domain set and y is the codomain set. What is there? For every x belongs to x, what is there? F inverse of f of x is equal to x, and f inverse of f inverse of y is equal to y for every y belongs to y. Using the composition of functions, we can rewrite the statement as follows. F inverse composite f is equal to idx, and f composite f inverse is equal to idy. Means here f inverse composite f means what? This one, f inverse of f of x is equal to x. Okay, whatever the x will be there, that value will be given here. F inverse composite f, that is f inverse of f of x is equal to x, and f composite f inverse of y, f composite f inverse of y is equal to idy here. F composite f inverse here, f of f inverse of y is equal to y. Whatever the value of y will be there, that will be put here. F composite f inverse and f inverse composite f. F inverse composite f is giving us x, and f composite f inverse is giving us y. Okay, it might be some confusing, but read it carefully. F inverse composite f is x, and f composite f inverse is y. Okay, here we can see f inverse of f of x is equal to x, and f of f inverse of y is equal to y. Why it is? Because f of x is equal to y and f inverse of y is equal to x. Okay, hold this bracket, this one is equal to x, and whole this bracket is equal to y. Okay, are you getting it? This is the simple inverse functions and composition of inverse functions. Then we already have seen normal composition of functions also. Then types of functions in the very first lecture that we have covered. What is complex functions? That also we have seen. In complex functions, the I, that is square root of -1, is there. Functions are depending quantity on another variable. Means two variables are there and they are depending on, means first quantity is depending on the another quantity. So the functions are centralized object of mathematics. Okay, so here we have completed this unit. all the bits which were given in syllabus that are covered here. So can we move towards the next unit? Tell me, have all of you gone through the MCQs for chapters 1, 2, and 3 given in teaching diary? Yes? All of you have got that link? All of you have got that link of MCQs for chapters 1, 2, and 3? It is given in teaching diary. You can see there. It completes our 5th unit. Now we'll start with our 6th unit. Name of this unit is algebraic systems. So what are algebraic systems? That also we are going to see. And along with that, the contents of this units are semigroups and monoids, and properties and examples of semigroups and monoids. So firstly, we'll see here what are the algebraic systems. Different types of algebraic systems we are going to see hereafter in the syllabus. 3 units are remain. So all these 3 units contain some types of algebraic systems and properties regarding that, and examples regarding that. So firstly, we will see what are the algebraic systems. A set A with one or more binary closed operations defined on it is called an algebraic system. Okay. Now a set A. Okay. A is the any set with one or more binary closed operations. Now what the closed operations meaning is, that word is very important. Binary operations defined on it, which are closed there, means what? In that set only, whichever we are taking 2 elements and operation, that specific operation performed on that 2 elements, and the answer coming from that, that answer also there in the same set, that is nothing but the closed operation. Okay, binary closed operation. Whatever the set is given there and the operation performed, specific operation which is given there, when that operation is performed on any 2 numbers in that set, any 2 elements in that set, and the answer is coming there in that same, and that answer is present in that same set only, then that set will be known as algebraic system. Okay. Example, what is given here? N plus. Okay. N plus means again what it is? N is the set of natural numbers 1, 2, 3, 4 like that, and up to infinity. We don't know what is the end of that set N. Okay. N is, and operation performed there is plus operation. Okay. Plus operation, I take any 2 numbers, 1 plus 4. 1 plus 4 is equal to 5. Is there 5 present in that N set? Yes. So it is a closed operation. 1, 2, 3, 4, it is up to infinity. So if I take any 2 numbers, 100 and 200, The answer coming is 300, and that 300 is also present in the set of natural numbers, that is capital N. So that operation is so that set is called as algebraic system. Are you getting the basic of that algebraic system? Yes. That word is very important, binary operations, but it should be closed. Are you getting? The next example is z plus minus. Z is what? Z is set of all integers. In that, it contains negative numbers also and positive numbers also. So it starts from minus infinity, given minus infinity up to -1, 0, and again positive integers are there, 1, 2, 3, 4 up to infinity. Okay, from minus infinity to plus infinity, it is the Z set of all integers. Okay, what is there? Plus operation is performed there. If plus operation is performed, if I take this one, -2 plus 2, okay, -2 plus 2, it is giving 0. 0 is present in the group. Okay, then I perform, suppose, -5 plus 4. Okay, again the answer coming is -1. It is present in the set, so this will be called as the algebraic system. Same case with minus operation. If I perform minus operation on any two numbers, 3 minus 1, it is giving 2. 2 is present in the group. Okay, minus operation, consider 3 minus 2. Sorry, 3 minus -2. Minus operation, I'm considering this 3 and this -2. Okay, what it will be? 3 minus -2 means 3 plus 2 is equal to 5, and 5 is present in this group, set itself. So here Z plus minus is also the algebraic system. Okay, then consider R plus dot minus. Now what R is? Set of all real numbers. What does it include? All positive, negative numbers, 0, including decimal. Okay, decimal points are also there. Then what should be there? R is set of real numbers. Means it starts from, again, positive and negative numbers, same set as this Z also, but including decimal points, means 0.1, 0.2, 0.3, 0.4, like that. Okay, it is only these are only the integers, but set of real numbers contains decimal numbers also. So and it also satisfies all these properties, like plus operation on real numbers is possessing there. Then dot means what? Again here, product of two numbers. Then minus means again subtraction. It is also performed on real numbers. The answers coming from these operations are there itself in the real number set. Okay, so what is there? R plus dot minus is an algebraic system. Okay, it is the example for that. Then binary operation. What is binary operations here? The binary operator star is said to be a binary operation. Star may be anything. Okay, star is just a notation here. Star may be plus, star may be dot, star may be subtraction. Okay, star is just the notation here. Starचं meaning काही पण असू शकतं, addition, subtraction, multiplication, division, whatever it will be, is said to be a binary operation, closed operation on a non-empty set A if A star B belongs to A. Whatever the operation will be there that performed on two numbers which are present in that set, and answer of that operation is belonging to A. For all AB belongs to A, AB are the set of elements of set A. It is the closure property or closed operation. Okay, how does it called closed operation? A and B both are in set A, and whatever the operation performed on elements of set A, answer of that operation is also in the set A. That is nothing but it is that star is called as closed operation, and the property is called as closure property. What the example? The set N is closed with respect to addition and multiplication, but not with respect to subtraction and division. N here we have already seen. N is set of natural numbers 1, 2, 3, 4. It is closed with respect to addition and multiplication. Addition we have seen already. Multiplication is also possible. 4 into 2 is 8, 4 into 3 is 12, or 2 into 4 is 8, like that. But what about minus, that is subtraction and division? Because if in subtraction and division, the order is important. In subtraction, suppose I take 1 minus 2 and the answer coming is -1. -1 is not there in the set of natural sets, isn't it? So what we can say is N is closed with respect to addition and multiplication, but not with respect to subtraction and division. Okay, it is the difference. That is, closure property is very important. Okay, in case of these algebraic systems. What are the properties of now algebraic systems? Individually also we are going to see when we are going to see the monoids and their properties. But collectively as algebraic systems, what the properties they possess is commutative. Commutative means again what? Let star be a binary operation on a set A. Okay, star be a binary operation on a set A. Star will be any operation. Okay, star will be any operation. It may be plus, means it may be addition, subtraction, division, multiplication. The operation star is said to be commutative in A if A star B is equal to B star A for all A, B in A. Okay, when the commutativity will be there, if A star B is equal to B star A. How it is going to be there? A star B is equal to B star A. In case of multiplication, in case of addition, it is possible. Order cannot matter there. 4 into 3 is equal to 3 into 4. Both the sides are equal. It is going 12 is equal to 12. For all A comma B in A, it is possible for two operations, that is addition and multiplication. In that case, the algebraic system is commutative. Okay. Then what is the associativity? Associativity will be, let star be a binary operation on set A. The operation star is said to be associative in A if A star B star C is equal to A star B star C for all A comma B comma C in A. Okay. Now, associativity again, dealing with the order of the elements. Okay. Again, addition and multiplication are the operations. Those are going to be satisfied here. A star B. So if it is the case that if I perform operation between A and B first, and result of that operation is again operated with C, is equal to B and C are operated first with the star, whatever the operation will be there, and result of that B star C is again operated with A. If both these sides are equal, then the binary operation on set A is associative. Okay. Again, as I told, addition and multiplication are the associative operation for all A, B, C in A. Whatever the elements in any order will be there, it will be associative. If any if we change the order, it doesn't matter on the result. Okay, it doesn't affect the result. Then identity, the main very important property is identity. What is there? For an algebraic system, A star, for an algebraic system, A star, an element E in A is said to be an identity element of A if A star E is equal to E star A is equal to A for all A in A. Okay. E is the any identity element. What is the property for that is, what is the condition for an algebraic system? A star, okay, is the set of numbers whatever, and star is the binary operation performed on that set. Then an element E in A is said to be an identity element. E is the identity element, okay, from set A. It is identity element. How it is identity element? A star E, okay, A star E is equal to E star A, means commutativity is there, and it is equal to A. It is means it is operation performed with this element, identity element. It is not going to change the element, any element in A. Okay. So that E will be called as identity element. Okay. Suppose here we take the set of natural numbers. Okay. I'm giving the example. Natural number set is there. And E is what? E is identity element. We are going to perform the multiplication operation. Okay. Multiplication operation. In that case, 1 will be the identity element, because we know whatever the whichever the element will be there, that will be multiplied by 1 is giving the same element. I take 5 into 1 is equal to 1 into 5 is equal to 5. It is giving the A itself. Okay. It is giving the A itself, whatever the element we have taken from this set A. Okay, set of natural numbers. Getting? If I take the operation multiplication, then in that case, what it is 1 is the identity element. Okay. For all a in A, whatever the value of A will be from 1 to infinity, 1 is the identity element for that case. Means if we take the multiplication operation on natural numbers. Note here, what is the note? For an algebraic system A star, identity element, if exists, is unique. Okay, if this exists, it is unique. Means again, what we can say is 1. 1 is unique element of that set, natural number set, because no other element is like that. If that is multiplied by any element and that giving the answer same as the uh, element that we are going to operate, only 1 is there. So from that example we can say that identity element is unique. Okay, identity element is unique. Only one identity element will be there if it exists. Not for all algebraic systems this identity element exists. We cannot take it for subtraction and division operations also. We can take it for addition operation. What will be the identity element? Can anybody tell me? If I take the set of integers and I take the addition operation, then what will be the identity element? Yes. What the identity element will be for operation addition? It will be 0. Okay, 0 added with any number giving that same number. So it will be the 0 for addition operation in case of set of integers z. We have seen this z. Okay, if we take addition operation on this set z, then the identity element will be 0. Okay, then the next property is inverse property. Let A star be an algebraic system with identity E. Let E be an element in A. Let A be an element in A. An element B is said to be inverse of A if A star B is equal to B star A is equal to E. Okay, what the inverse property is? A star B is equal to B star A is equal to E is the identity element there. And if B is inverse of A, then A operated with its inverse is equal to its inverse operated with A is equal to E. Is equal to E. If it is the case, then inverse property is possessed there on the algebraic system. Okay, E is the identity element, A is any element, and B is inverse of A. Instead of writing A inverse, it is written here as B. Okay, B is said to be inverse of A if A star B is equal to B star A is equal to E. It is the inverse property. Then the next type of algebraic system is semigroups and then monoids. Then it completes the unit there. We will see this in the next lecture, that is on Monday. Okay. just for any algebraic systems, all these properties are there: commutativity, associativity, identity, and inverse. And then again, what it is, if for semi groups, again two properties are there: closure and associativity. Then for monoids, again, if it possesses identity and closure and associativity, then those are called as monoid. Like this, the properties are there. The properties the systems possess, uh, different properties. From that, its types are there. Okay, monoids and submonoids and semigroups, like that. Groups are also there. The next unit of this algebraic systems is groups. Okay, then lattices are there. Those are in the next units that we are going to see. For now, we will stop here and we'll see the next part in the next next lecture or next session. Okay, so we'll stop here today. On Monday, we will see the next part.